Hello.
Hello, Dom. Hello, Macaulay. Hello, Jake. Hello, Nathan. Or Nathan.
Hello. Hello.
How are you all
Hello.
doing?
All good.
Yeah, all right.
Good. Who we got left to come? Connor? Taylor? Who were here this morning? We've got a couple of minutes yet. How'd you get on with Adrian then?
Yeah, not bad. We just discussed what we're going to do about our presentation
Yeah.
and all that stuff. So
he didn't have to do any writing on the screen like me, did he?
no, we can just go off and crack on with it for the most part.
Yeah. Yeah. Did he keep popping back, did he?
No, we just left it and just did our own thing.
Oh, okay, yeah. Yeah.
Which it works with projects because you have your specifications, so you can just work through it bit by bit.
Yeah. Yeah. I think I might be a little bit better this time because what I'm going to do is share the whiteboard from my iPad because that's a different menu for selecting the pen and the pencil and the colours, and it doesn't get affected by my wrist, so that might help a little bit. Is my audio clear, guys, by the way? Because I didn't know if that's a bit distorted last time.
Oh, I think it's the same.
Not too bad, yeah.
That's
Yeah,
good.
that's right.
Okay. Yep. Oh, we got Taylor now. We're just coming.
Hello.
Afternoon, Taylor.
Good afternoon.
How you doing?
I'm very well, thank you. Yourself?
Oh, not too bad. Just hoping to be a little bit tidier this afternoon than it was this morning. That's all. I don't really make too much difference because we've virtually started again now anyway. So we're talking about parallel RL circuit. Yeah. We've got a single voltage feeding both common to both components. Yeah. There'll be a current IS flowing there, a current IR there, and a current IL through the inductor. Yeah. Phasor diagram wise, because the voltage is common, the voltage is our reference phasor. Yeah. Whereas in the series circuit, that was the current that was the reference phasor. And then we've got the current IR, which is the in-phase component. Remember, current and voltage on resistor are in phase with each other. And then lastly, we've got our IL down here at minus 90 degrees or minus pi/2 radians. Yeah. And then we can complete that there on the phasor diagram, and our resultant down the middle is IS. Yeah, all okay with that now. And our angle of IS is this one in here. Yeah.
Yeah.
Right. So we could find, could do these calculations the longhand way. So we could use Pythagoras theorem. To get magnitude. of IS. Yeah, and then use the tangent to get the angle. And we've done plenty of that. But what I wanted to do, we're also in this, if we can calculate IR from V over R. Okay, we can calculate IL from V over XL. We'll get to that in a minute, the capacitive reactance. So what I'm trying to say is a number of different ways you can calculate things in the end. All right. But what I'm going to do is we're going to look at a proper example with some numbers now, and then we'll do that the complex number way.
What does that say on the bottom left?
Bottom left. Tangent. Here. Tangent. Hang on, I'll rub that out and rewrite it. Okay. Yep.
Yeah.
So that's the phasor relationship in a parallel RL. So we've got a lagging current overall because we've got an in-phase resistive current and a 90 degrees lag and inductor current. Yeah. So on the next page, you've got a problem. I'm going to save that first. So we've got a 20 ohm resistor. In parallel with an inductor of, excuse me, 2.387 millihenries. Supply voltage is 60 volts, 1000 hertz. Yeah. And the problem says calculate the current in each branch, so it wants to know IL, IR, and IS. Yeah. And it also says wants to know the phase angle, which we'll find, and the circuit impedance. All right. So anyone got any idea where we could start in solving one part of that problem? Bearing in mind we want to find IL, IR, IS, and ZT.
Get IR, do V over R.
Yeah. So IR is the V over R, 60 over 20, which is 3 amps. Yeah. For completeness, the angle of that is 0. Yep. Having done that, what can we do next? So that's A done on our end, because we want, what we need to do to find IL.
We need to work out XL.
Yeah, good start. You realised we can use Ohm's law. I'll just put it down here. We can do Ohm's law. IL equals V over XL. But first of all, we need to find XL. How do we calculate that?
Let's have a little look.
Anyone remember?
We'll have a recap.
Yeah, have a wee check.
XL equals 2 pi
2 pi
L.
F.
L. Yeah,
Oh,
well done.
Is it L or is it C?
Just 2 pi times 1,000 times 2.387 times 10 to the minus 3. Push some buttons.
Where'd you get 2,000 from?
2 pi times, that's 1,000. Does it look like 2 to you?
Oh, sorry.
That's all right. I think I'm probably going to have to write a bit bigger and use a few more pages.
Yeah, that'll be right.
Should get 4 amps, yeah? Anyone got that yet? So IL is 60. What a 2 pi FL come out at?
$15 ohms.
Yeah, I didn't get.
So this is 15 ohms.
Yeah.
So that's 60 over 15. The angle of that inductive reactance is what? Per inductor.
90 degrees lagging.
Plus, yeah. No, the inductive reactance is a positive 90-degree angle. So then the current will come out lagging because we've got to do 0 for the voltage. So that's going to be 4 amps angle minus 90 degrees. Yeah, and that's what we'd expect for the current in a inductive circuit. Yeah, it's lagging. All agree?
Yeah.
Yep.
Yeah, good. So what we can then do is we need to add those two currents together. Now, what's our favorite way of doing that?
Separately.
IR is equal to 3 angle 0 degrees. IL is 4 angle minus 90 degrees. Convert them to rectangular and they equal. So this IR one, because the angle's 0, it must be 3 plus 0j. Because this is minus 90 degrees, there must be no horizontal part and a minus 4j. Everybody follow that or not? If you need to use your calculator to check that, please do. Yep, all happy? And therefore, IS is equal to those two added together. So that's 3 minus 4j. And then we can do 3 minus 4j, convert that back to polar form for our final answer. I get 5 amps angle minus 53.1 degrees. Anybody else got that?
Yep.
Yeah? Good. So we've now calculated the two currents, the supply current, and we got the phase angle because we got that on the complex number. So you see how going down the complex number route actually does all that for you. Yeah. Instead of doing them all separately. The last bit that's asking for is impedance. So ZT, the total impedance, is the in phase part R plus XL J ohms. That's how we calculate that. Do you remember that from before?
No.
No.
No, a lot's gone on since then.
Yeah, I understand that, and that's why I'm putting them up there at the moment. But I'm just asking the questions, so that's not just me rabbiting on all afternoon. Our resistance is 3 ohms. Our inductive reactance was 4 ohms, was it? No. Resistance, sorry, is 20 ohms. And inductive reactance, just remind me what that was because that's on the other page. 15, wasn't it?
What's
Yeah.
that?
Inductive reactance,
Yeah.
15 ohms one.
Yeah.
20 plus 15j ohms, and we could just do a straight convert to polar on that. For Z is equal to hang on, whoa. Anyone notice what I've done wrong here? Bet you can't. These are in parallel, not series.
Oh, just about to say that.
Yeah. Right.
Yeah, I was just eating my
Never
apple,
mind.
so I didn't have time.
We all make mistakes. How are we doing for time? 28 minutes, so we should have time just about to do this.
Since
So-
Z equals RT bracket XL minus XCJ.
Yeah, that would be if they're all in series, but these are in parallel. So we've got to do R times XL over R plus XL.
Uh,
Yep. So up the top, we got R, which is 20 ohms, angled nothing, times XL, 15 ohms, angle 90. Agree with that?
yeah.
Down the bottom, we'll go in, we'll keep it in rectangular form for the moment. So we've got 20 plus 15J. Yep. And then the top line, we do 20 times 15, 300 in it. Yeah. Angle, 90 degrees. Then underneath, we got to convert 20 plus 15J to polar form because we want this in polar form to do the division. So that make it easier. So 20 plus 15J now in a polar form. $25, anyone get? Angle 36.9 degrees. So that's 300 over 25. 12 ohms angle. Then we've got to take 36.9 away from 90.
$53.1.
53.1. All right. Yeah.
Yep.
So
Sorry.
using complex numbers, if you can get the hang of them and you remember about the rectangular being specifying the vertical and horizontal components, the polar form is the length of the resultant plus at whatever angle it is, and make these calculations work a bit better. Can you see that warning that we're running out of time?
Remaining meeting time 6 minutes 54.
Yeah. No, I've got a warning on my screen saying we're running out of time. You can't see that, I take it?
No.
No, that's all right. What I just want to do, what else we got next? Parallel RC. Right. Very quickly, how much time has gone? 6 minutes. Just want to very quickly unsave that screen. Yeah, save all them. Stop the share there. I'm just going to share with you another screen here, which is the circuit simulator. Just to show you how briefly we can confirm these results. I've already set it all up. So can you all see that?
Yeah.
Yeah. So I've put in a AC source here, 60 volts, and inside that 1K. Yeah. I'll put an ammeter in for IS, IR, and IL, and I got the inductor and the resistor in parallel. Yeah. Just show you do an AC simulation. Now, although we're only interested in 1 kilohertz, that's like I asked for a start and stop frequency for a sweep. So you have to put at least 2 in. So I'll put 1K in, put 2K in, and a step of 1K. So we got 2 steps. So we'll get 2 sets of results, one for 1 kilohertz, one for 2 kilohertz, which I've already done anyway. So that's how you'd set that up. And that's a way that you could, if you got the circuit simulator, check some results. Now, I need to go over here. And we can see now, this is the 1K frequency, 1 times 10 to the 3. We've got an IS of 5 amps at angle minus 53.1 degrees. IR is 3 amps, no angle, but IL is 4 amps, angle minus 90. And they're the results that we got. So it just kind of confirms that through simulation. We'll stop that share now, save that screen, and I'll be back with you within about 5 minutes, all right?
Beautiful.
All right?
Hoorah.